MathRock's channel. In this video, you will learn about the infinite geometric series. And before we start with the infinite geometric series, let us talk about the infinite geometric sequence first. So an infinite geometric sequence is actually a geometric sequence. So you are already familiar with these terms that actually presents a geometric sequence. Since that the sequence actually has an ellipsis here, this suggests that the geometric sequence actually goes on forever. And to give you an example, here we have a geometric sequence for which the common ratio of the sequence is positive 3. And again, this geometric sequence ends with an ellipsis. So again, this suggests that there are infinitely many terms in this geometric sequence that follows that particular rule. And now let us proceed with the infinite geometric series. So you know that a series actually pertains to the sum of the terms of a certain sequence, for which here we would like to have the sum of the infinite terms in an infinite geometric sequence. And just to give you an idea, let us have this example. So here are the first few terms of a geometric sequence. But here we would like to find the sum of all the terms. But there are infinitely many terms in this infinite geometric sequence. And here is the formula for the infinite geometric series, which happens to be S. And we have here the symbol for the infinite. So we are trying to get the sum of all the infinite terms in an infinite geometric sequence, which happens to be equal to a sub 1 all over 1 minus r, where we have the value of the common ratio be greater than -1 but less than +1. Or we may also say that the absolute value of the r is less than 1. You have also learned that in the definition of the common ratio, it is actually a non-zero real number. So here in our first problem, we would like to find the sum of all the terms in the given infinite geometric sequence. Now, there are only two quantities that we would like to know based on our formula, and those are the a sub 1 and the common ratio. So once we take a look at those information in our problem, we have our a sub 1 be equal to -2, while the common ratio be equal to the second term divided by the first term, which happens to be 4 divided by -2, which actually gives us -2. Before we actually start with the substitution process, let us try to make an inspection first with regards to this value of the common ratio, which happens to be equal to -2. So the condition for us to apply such formula for the sum of the infinite terms in a geometric sequence is that the absolute value of r should be less than 1. So here, if we take a look at this value of the common ratio, which happens to be a -2, so the absolute value of this -2 is actually a +2, for which it actually gives us a false statement because +2 is not less than 1. It is actually greater than 1. Okay? So it is actually a false statement. So that means we will not apply such formula for us to find this sum of all the terms in this given infinite geometric sequence. So anyway, this formula is only applicable for such condition about the value of R. Anyway, just to give you an additional information, this formula is only applicable to convergent series. And now, this formula is not applicable for this divergent series. And let us proceed immediately with our next example. So here we would like to find the sum of all the terms in the given infinite geometric sequence. So let us try to do some inspection first with regards to the value of the common ratio. And we can easily have the value of the common ratio by dividing the negative 6 by negative 2, which happens to be the second term divided by the first term. So we have negative 6 divided by negative 2, and that gives us a positive 3. Again, the absolute value of positive 3 is actually greater than 1. So it gives us another false statement. And we cannot apply this formula for this one because this is a divergent series. Let us have the next. Here we would like to find the sum of all the terms in the given infinite geometric sequence, and here is our sequence. You might have noticed that in our first two examples, if you take a look at the absolute values of the terms, so let me go back with this example right here. So if you take a look at the absolute values of the terms in this infinite geometric sequence, you may notice that the terms with respect to the absolute values are actually increasing. And once we go back at the first example here, that gives us the same situation. While here on our third problem, you would notice that the absolute values of the terms in this geometric sequence are actually decreasing. And let us check what happens with regards to the value of the common ratio. And let us have the common ratio. So having the second term of 32 divided by the first term of 64. So here we have our common ratio be equal to 1 half. And now, let us have the absolute value of 1 half. So the absolute value of 1 half is 1 half, which is actually less than 1. So it gives us a true statement. So since we have satisfied this given condition for the common ratio, then we can apply such formula for the sum of the infinite terms of infinite geometric sequence. And now, having the first term of positive 64 and our calculated value for the common ratio is 1 half. Let us substitute this information to the respective variables in the formula. So we have our a sub 1 be equal to 64, and we have our common ratio be equal to 1 half. So now let us start with the denominator. So here, 1 minus 1 half is 1 half. And applying our knowledge on dividing this kind of numbers, then we must first write the numerator as it is, and we multiply the reciprocal of the denominator. So meaning we are just interchanging the position of the numerator and denominator. So here we have 1 half, and we will be writing this as 2 over 1 or simply 2. And multiplying 64 with 2 gives us 128. So that means that the sum of the infinite terms of this infinite geometric sequence is 128. And let us proceed with our next example. So here, You can easily notice that the absolute values with respect to the terms of this infinite geometric sequence are actually decreasing. And let us do some inspection here. So we can easily find the value of r by having the second term of -2 divided by the first term of +8. So we have our common ratio be equal to -1/4. So here, the absolute value of -1/4 is actually less than 1. So we may use this formula for us to find the sum of the infinite terms in the infinite geometric sequence. So having the sum of the infinite terms, which happens to be equal to our a sub 1. So again, your a sub 1 based on this sequence is +8. And this will be divided by 1 minus the value of the common ratio. So we have this value of -1/4. So let us start simplifying this expression on the right-hand side of the equal sign. And we have 1. So 1 minus -1/4 is actually 1 plus 1/4. So, and it actually gives us 5/4. So again, how did we get the value of 5/4? Let us do some scratch work here. So just to remind you of the process. So we have 1 plus 1/4. So the LCD of the denominators of the invisible 1 right here and the +4 is actually a 4. And now dividing the 4 by each of those denominator, here we have 4 divided by 1, which is 4. 4 divided by 4, which happens to be 1. And multiplying those quotients to their respective numerators, here we have a +4. Here we have a +1. So adding those numerators together, we have 5. And the fraction would be 5/4. And now, dividing this fraction gives us 32/5. So anyway, let's take a look at it this way. So writing the numerator first, writing the reciprocal of 5/4, which happens to be 4/5, and multiplying these two numbers together, we have 32/5. So that means that the sum of the infinite terms of the infinite geometric sequence is 32/5.